Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is ET 123, Digital 3. Today we're going to discuss ADC, analog to digital conversion. You're taking an analog signal and converting it to a digital quantity. Okay, so our previous lecture where we discussed the basics of DSP, we had our, well, first off, obviously we had our analog signal, and then immediately following the analog signal it goes into is basically our filter. It could be a low pass filter, high pass filter, band pass filter, stop filter, something like that to get rid of the junk that you don't want to go ahead and be converted into digital. And then you've got your sample and hold. And if we remember, our samples are occurring at certain intervals, ideally twice as fast as the natural frequency of whatever we're trying to sample because of the Nyquist sampling theorem. And we're sampling it at that value, and basically we're holding it that value until the next sample comes along. And then we hold it at that value till the next sample comes along, and hold it at that value till the next sample comes along. That's the basis of sample and hold. Take a look at it, and for all intents and purposes, it stays at that value that you looked at it until you look at it again. Okay? And now we are kind of into the ADC portion of it. Analog to digital conversion. So we did the filter, we did the sample, we did the hold, and now we're doing the four-step ADC, which is quantization. Okay, quantization means basically you're assigning a quantity for that analog value, a digital quantity for that analog value. Okay, say we have a wave that looks like this guy right here, like that guy right there, and we are going to go ahead and sample it using a 2-bit code. And our 2-bit code can obviously take on values of 0, 0, 0, 1, 1, 0, and 1, 1. And this is our analog signal that we're going to try to stuff into these 4 categories. And you can already see what's going to go on here. With only 4 categories, our digital approximation of this, our end result, is not going to look as pretty as our analog version of it. Okay, so if you're trying to take this analog thing and divide it up into one of these 4 categories at every moment in time, it's not going to look so good. But now, imagine if you had a 3-bit code where you are capable of now dividing it up into 8 blocks. It might look a little bit more like the analog. It's still kind of blocky. Now imagine 16 different divisions. And now where I can take one of 16 values. So you've gone from 4 to 8 to 16. Basically, the number of bits you have is making your digital approximation look that much closer to your analog version. This is the progression, from block man to stop sign man to quasi pixelated version of Pac-Man. And then you've got, like 64-bit high definition, 3-dimensional virtual reality Pac-Man with 64 bits. Basically this is the evolution of the Pac-Man species. Okay, so as you're getting the picture here, basically the number of bits that you're trying to shove an analog into, the more bits you have, the better approximation you're going to get there. Okay, so let's just go ahead and do this little analog signal right here. And let's say we're going to sample it twice, we're going to sample it way faster than the the naturally occurring frequency of this. We're going to sample it right here, right here, right here. Well, actually, here, let's do it even slower than that. So at every point right there, we're just going to go ahead and sample and hold, sample and hold. So we're breaking this thing up into a digital approximation. I'm going to go ahead and do the rest here. We're basically breaking it up into a bunch of samples that have been held at that particular value from the moment it was sampled until the next value. And then at each point, what we have to do is to divide these particular values into our 4 particular windows, 0, 0, 0, 1, 1, 0, or 1, 1, okay? And for the purposes of argument, let's just say for it to be a valid 0, 1, it's got to be above this level. And for it to be a valid 1, 0, it's got to be above, let's pick some value. That's not going to work out so good. Let's raise that up. There we go. That represents a little bit fairer divisions there. So for anything to be above, labeled as a 1, it's got to be above this value right there. Anything to be labeled a 1, 0, it's got to be labeled at that value right there. And anything to be stuck in the 1, 1 bin, it's got to be above that value. So at this point right here, our first sample, it's not above a 0, 1. So our digital representation is a 0. These guys right here are both above our 0, 1 value, but they're not quite 1, 0. Same thing with this guy. Got there, here. This guy's a 0 because he hasn't quite made it. This guy, let's just go ahead and make him a 1. Let's make that guy a 1. But now here, this guy is above this. So we're making him a 2 or a 1, 0. This guy, he has made it above. So he's a 1, 1. Same thing with that one. This one is a 1, 0. And this guy, what is he? Let's make him a 1, 0, 1. Okay, so now, this is messy here. What's represented, our digitization of this, our quantized digital value, is our green. And I know it's kind of messy right there, but our blue is our original analog signal. But I'm going to go ahead and take my yellow highlighter, and our digital representation of our blue is that right there, which kind of looks like our blue. Not exactly, though. And that's what I've drawn right there. It's just a little simplified version of it without it being all messed up. So that's our original analog, and here's our quantized digital version of it. Kind of the same, but not exactly. It's got a little rise there, just like that guy's rise, bigger rise right there. How would we get this more accurate? Well, again, we're kind of still in block territory. We're only using 4 bits. Use 8 bits. You might get a finer representation of that. You might get something that looks like something like this. You know, that's our 4-bit representation of it. Excuse me, here's our, I'm saying bits, I'm sorry. That was our 2 bits. Here's our 3 bits. I meant maximum of 4, maximum of 8. And now here's our 4-bit representation, maximum of 16. You know, you might get something pretty close to it. And there's, trust me, there's little digital edges to that one right there. Okay, so you see what's going on there is the more bits you've got, the closer the digital representation is to the analog. Additionally, you could be sampling this at a faster rate. Notice particularly this area right here where it's a pretty steep slope. You would probably want to have faster samples there because notice we're only getting that and that right there on the edge. Whereas this guy with 4 bits, you're getting a better sample. When it's fast, when it's changing so fast, you want to sample it a little bit more. So how do you get a more accurate representation? Increase the number of bits that you are trying to categorize it into and sample it a little bit faster. Okay, so I think that's pretty much it about the general of ADC, analog to digital conversion. And if you want to think about this as measuring, you know, just measuring with a ruler with only 1/2 inch increments. This guy's got 1/4 inch increments. This guy's got 1/8 inch increments. You know, just you're getting a more detail picture this way. But if you are up this way, this is a lot easier. You know, you're getting a general value, general indication of what's going on. It's easier, but far less detail. So let's move on to the next section of this lecture, where we actually talk about analog to digital conversion methods, of which there are 4 main topologies or methods. It's just a fancy word for methods. The first one is flash, which is different from flash memory. This is also called simultaneous. Second one is dual slope. Third one is our successive approximation. And our fourth and final method, which we'll discuss, is our sigma delta conversion. But before we do that, let's do a super compressed version of EET 221 and 222, of which we're not going to go into major details. But if you had 221 and 222, you can kind of skip this portion of the lecture, but this is just a 5-minute walkthrough of what an op-amp is. So an op-amp has 2 inputs, the non-inverting, the inverting, signified by a minus, and our non-inverting, signified by a plus. And then it's got 1 output, and that's at the point of the triangle. Okay, so the op-amp, and this is without all the junk, without all the great stuff in EET 221 and 222 can be summed up as follows. It is a magic device. See, don't you wish you just had that word when you went into 221 and 222 and just forget all the rest? It is a magic device that holds the inverting and non-inverting at the same potential. And no current goes into the op-amp. Okay, so I just summed up EET 221 and 222 into 2 sentences. Again, first sentence, the op-amp is a magic device that holds the inverting and non-inverting inputs at the same potential, and no current goes into it. Okay, so why is this so special? Okay, think about this. We've got our inputs here, and our non-inverting, let's say it's held to ground. Here's a resistor Ri, and here's a V in. Now watch this. RF. That's a feedback resistor. RI, our input resistor. So, using our first sentence there, okay, it holds inputs at same potential. Okay, so making use of that, holds inputs at same potential. If our non-inverting's at ground, our inverting should also be at ground. That's called a virtual ground. Okay, so no stretch of the imagination there. But now what happens when that point right there is held at ground? Well, if we apply a certain voltage to Vn, whatever it may be, +5, whatever, +8, there exists a potential gradient across R1, which will cause current to flow in that direction. And that current, I, is equal to Vn divided by Ri, okay? Because this potential's at ground here. That's at ground. And current's going to flow in that direction. But we've just learned that number 2, no current into the op amp. So if there's no current going into that guy, and current always has to flow in a path, right? It doesn't just flow in one direction and stop and the electrons just hang out waiting here. That doesn't happen. It's got to flow. Where's it going to flow? It's going to flow through RF. So now, what's the difference between the current flowing in RI and RF? Well, according to Kirchhoff's current law, there's no current leaving this node going into the op amp. So that means that same current is going through RF. So if you've got current flowing through RF, that means there will be a voltage drop across RF. Aha, so you see what's going on now. So if there's a current flowing through RF, there means there's a voltage drop. And according to our conventional definitions, if that was at 0 volts and current is still flowing in this direction, it means that there's a lower potential here. And what is that lower potential? Well, if it's the same current I times RF, okay? And because it's a lower, basically, negative V out is equal to the same current times RF, okay? So now we can rearrange that by putting this guy right there, and ultimately, you're going to get where there's a bit of a gain there, well, depending upon the arrangement of the resistors, but the negative sign indicates inversion, okay? So this little micro lecture here that I just gave about this whole stuff right here, I don't know why I just introduced it into analog to digital conversion. It's not so important for analog to digital conversion, but it is important for digital to analog conversion. So just remember this for right now. And plus you've already had some experience with this in EET 221 and 222. And if not, you just got the 2-minute lecture for what would normally take you 6 months to understand. There is a little bit more to this too. But keep this stuff in the back of your pocket for, especially when we get to digital to analog conversion, DAC, okay? So let us talk about our first analog to digital conversion method. And that's flash, also referred to as simultaneous. Okay, so flash uses voltage comparators, which are kind of like our op amps there. So all that hocus pocus I just did right there actually is a lot simpler in Flash. So we've got a voltage comparator. Again, it's the same symbol too. We got an inverting, non-inverting, and our output. Voltage comparator. And the deal is, with a voltage comparator, if the positive input exceeds the negative input, there's a high output. If the negative voltage is higher than the non-inverting input, you're going to have the opposite case, a low. You can also put them up this way. So let's, I'll just give you an example here. If that's 8 and that's 5 volts, what's the output of this guy? Well, its non-inverting input is exceeding its inverting input, so it's a high. So now, what's that? Well, it's a not the conditions we're looking for, so that's a low. Okay? So that's how our general purpose voltage comparator is used. And we use these in the 555 lectures. So now, making use of a bunch of these types of voltage comparators, we can create an analog to digital converter. And the advantage of Flash is it's basically the fastest and the simplest means of doing it. It's the highest throughput. This is basically used for communication devices when you need to speak and convert and someone needs to hear you immediately. Think of your cell phone, radio, telephone communications like that. You want no delay between the conversion of an analog signal to a digital. The disadvantage of this guy, it's using lots of hardware for higher resolution. So let's write those down. Advantage, fastest, and in my estimation, it's the simplest to understand at least. Highest throughput, because you're doing everything simultaneously. The disadvantage, lots of hardware, especially for high resolution needs. Okay, so let's go ahead and how do you use a bunch of voltage comparators for Flash? Well, first off, take a big long string of identical resistors. And why is the 555 timer called a 555 timer? Well, because there's 3 5K resistors in there. And according to the voltage divider rule, if they're 3 identical 5K resistors, they should each have the identical voltage drop across it. Okay, so same thing here for a Flash ADC. Basically, what do we got here? 1, 2, 3, 4, 5, 6, 7, 8 resistors here. And whatever this voltage reference here is, each one of those resistors, if they're identical, should have 1/8 of VREF drop across it. Dig? So just for argument's sake, let's say voltage reference is 8 volts. And each one of these things, regardless whether they're 10K, 5K, 2K, as long as they're identical, in this particular case R, each one of them is going to have a 1 volt drop across it. So what's the voltage here? 1, 2, 3, 4, 5, 6, 7 volts. Okay? Now, at those locations, put our handy dandy little voltage comparators where the negative, the inverting input is tied up to those. And now to complete this whole thing, all you need is every single one of these non-inverting inputs is tied together. And this guy right here, that's to our V in. That is our whatever we want, our analog value. I'm going to call it V analog. That's our analog signal. Okay, so now all these inputs, all these outputs from the voltage comparators are being placed into a priority encoder. Remember from that 74-148 lab, the priority encoder, where the highest number pressed is the only one that's displayed. So that's the whole point of a priority encoder. And let's say we have, so that's 7, and then you don't really need a ground, a 0 volts one. Let's say we have our analog value. This guy is enabled. At a frequency twice as fast as the naturally occurring frequency of whatever that analog signal was. And let's say it's sampled and it happens to be 3.5 volts and it's held at 3.5 volts. And now we are going to start quantizing it. So 3.5 volts. Everybody has 3.5 volts on the non-inverting input. Okay, so let's just go to 7. The one with the 7, this guy right here, 7 volts. We're going to zoom in on him, minus plus. Inverting input has a 7. Non-inverting input, everybody's got the same 3.5 volts. What's the output here? Well, my inverting input in this particular case is exceeding my non-inverting input. So that would be, what's going on here? A low. Same thing for the 6, same thing for the 5, same thing for the 4, and now we get to the 3. So looking at the perspective of the voltage comparator that's tied to, in this particular case, 3. The non-inverting has 3.5 on it. That one's going to go high. Okay, and because it's priority encoder, yes, I know that 2 and 1 are also going to receive 1s, but it's a priority encoder, so its output is 0, 1, 1, i.e. 3. Okay, so let's say, I don't know, 4, 4.1. Okay, so at 4.1, again, everybody's inputs are tied. Everybody's non-inverting inputs are tied to that 4.1. So yeah, 3 is still going high, but in between here, this guy is giving a high value. Okay, long story short is basically a flash, i.e. simultaneous analog to digital conversion. Everybody's looking at simultaneously, and according to what we just discussed, if everybody's looking at it, i.e. the number of bits you've got there, look at all that hardware that comes with it. Okay, so since we don't need a 0 to the n minus 1 comparators for the number of output bits. And by the way, that last output one would have been 100 MSB to LSB, saying I've got a 4, even though it's 4.1, my digital approximation is 4. Okay, so have we discussed everything we want to do about Flash? And I think we have. Okay, the next guy that we're going to discuss is dual slope. Okay, dual slope, analog to digital converters. Well, first off, uses a capacitor, which if you remember right, is an energy storage device. So, if there's a constant discharge rate, and you've charged up to a very high value, wouldn't it take longer for it to discharge than something charged up to a lower value? So that's the question to think about when a dual slope analog to digital conversion. So it's going to take longer for something to discharge if it's at a higher value than something at a lower value, which will discharge quickly, more quickly. So basically what you use is a counter to measure this time interval, okay? The advantage here, less stuff. Because in our flash version here, all those voltage comparators are simultaneously looking at our one input value, and a bunch of them are going to say yes, 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 and a bunch are going to say no, 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 I can't beat it. Whereas this guy, it's just got one, well, not really one, it's one circuit, basically, less stuff. Disadvantage, a lot longer to work, because if it's at a higher value, it's going to take that much longer for something to discharge, so it's slower than our flash method of analog to digital conversion. Okay, so a quick functional diagram of this guy. So here's our input, here's our negative reference, and that's critical. And here's a switch that can flip-flop in between these two guys. We've got our current limiting resistor. And here's that op-amp I was talking about, where the non-inverting is tied to ground, and in place of a feedback resistor, we actually have a capacitor. This is what's called an integrator or a ramp. The rest of this stuff is actually kind of not as important, but I'll show you what the important parts are. Okay, so we are starting off with, first off, that guy connected. That guy right there at 0, saying nothing's there. Counter is, oops, there's inputs there. There's nothing in the counter. Everything's all reset. And we go ahead and switch the control here. Goes ahead and says, okay, switch this thing to the input, V input. Okay, so now V input is going to cause current to flow and that capacitor is going to charge up, okay? And because we don't really know what that V input is, it's basically going to be a variable slope. It's going to be a variable amount. I mean, if it's a tremendous V input, tremendously large V input, don't you think the capacitor would charge that much faster? Let's go ahead and illustrate this in a diagram here. So this is time. And because this is, we have to account for that negative there. Say for a tremendously large voltage, and let's say we only let it do that for 4 seconds. So basically that's a key point too. It's a fixed sample period. So if it's a fixed sample period, okay, measure it for 4 nanoseconds. If it's a tremendously large voltage, that's going to ramp up like crazy. Okay? If it's an intermediate voltage, it's just going to go like that. If it's a low voltage, V input, it's just going to be like that. Okay? So now the question is, when that control circuit says, okay, we have reached the fixed sample period and we've charged to low, medium, or high, which was proportional to our V input. It's really not V input. You wouldn't want these tremendous, I mean, say it's 480 volts here, but it's proportional to our input. Now we go ahead and switch to our known negative VREF. Okay, now if it's a known voltage, whereas previously this was a varying voltage, whatever V input would be, it's going to change its slope. If it's a fixed voltage here, that means it's going to be a constant slope for discharge. See how the slopes on that first portion were a lot steeper for the higher voltage and more shallower for the low voltage? But during this period, it's a very constant slope because we're using that same negative VREF, whatever it may be. And all we're going to do, how long does it take to discharge? Well, the low only took 6 nanoseconds, whereas the medium takes 8 nanoseconds. The big long one takes 12 nanoseconds to discharge at a constant slope. Okay, so this portion of it, this side, fixed time, variable slope. That's the read, basically the sample portion of it. This portion of it here, constant slope, or fixed slope, whatever you want to call it. Variable time interval. And the key thing is the variable time interval is the counter. Okay, the time it took to discharge depends on its initial voltage. If the counter is basically just clocking along, okay, 8 nanoseconds, that means 4 volts. 12 nanoseconds, that meant 8 volts. So basically the counter records this time it takes to discharge, and it's indicative of the magnitude. All right? So one can immediately see, yeah, it took less stuff. There's only 2 voltage comparators here, one being used as an op amp, and a little bit less stuff. There's a couple more things here like a control circuit and our counters and latches, but substantially less than our flash conversion, But one could see, okay, it reached 480 volts or whatever it would be. It would take a long time to discharge. Its throughput is not nearly as fast as flash or simultaneous analog to digital conversion. Okay, the next one that we're going to discuss is our successive approximation means of analog to digital conversion. Not as fast as flash, but it's got a fixed conversion time. Again, less stuff than flash. Okay, so successive approximation. Basically, you start with a set of output values. And what you do, you take your input and you see if it's equal to the output. So you compare it with your input. If your output is equal to your input, you just happen to get super lucky right from the get-go, no need to convert because your output and input are equal. But if it's not, what you do is you just step down to the next successive level. And it's typically done MSB down. Okay, so basically if your input is greater than or less than your prescribed combination of values, you successfully work your way to the best possible combo. This is kind of like the optometrist where puts a bunch of lenses on your eyes and kind of brackets his way down to your exact prescription. You know, basically, which is better, lens 1 or 2? Well, you say, so 1 or 2. Well, I say lens 1 is better, and these are huge steps here. And so he goes, okay, so lens 1 is better. Now, which is better, 1A or 1B? And you're like, well, I think 1A is better. And now 1A I, 1A II, which is better? That guy. So basically, you're successfully working your way through these things and these macro steps down to your final micro step there. Okay, so how we can do this in the digital realm, not the optometry realm, is the following. Here's again, you're using your comparator. There's your input. And this is your previously stored output for your digital to analog converter. And this here is going to be our register. Okay, so let's say we're going to do, let's do 4-bit. So 2 to the 3, to the 2, to the 1, to the 0. And like I said, it's typically done from the MSB down. And we assign each one of these guys a weight. And just because we're going to keep it simple, 2 to 3 is assigned a weight of 8 volts. This guy, 4 volts, 2 volts, 1 volt. And what you do, your input, example of the book, is 5.1 volts. You start from the MSB and work your way down. So 1, 0, 0, 0 is the value of 8 volts on the non-inverting input, on the inverting input. What's the output for this voltage comparator when the non-inverting input has 5.1 on it? Well, 5.1 is less than 8 volts, so that's going to be a low. Okay, so now what that shift register is going to say, didn't work there, so 1, 0, 0, 0. Move on to the next one. The next guy, is going to be 4. So now it's telling that digital to analog converter, send 4 volts. Now what's the value of the voltage comparator? It's a high. Nice. So we definitely want to store 1 in that shift register, the 2 to the 2 position. Go on, and now you're going to try 0, 1, because we know that was a hit. That was good. Because we're moving MSB to LSB. Now is 0, 1, 1, 0. 6 volts. Is it equal to 6 volts? Nope, because 6 volts is higher than 5.1. So that's going to be a low. So that didn't work. But now, move on to the LSB. We already figured out that 4 works. Does 5 work? Now we send 5 volts there. Yes, it does. Our nearest approximation for this successive approximation means of analog to digital conversion is 0, 1, 0, 1. How many steps did it take? It took, well, I already erased one. 1, the one that I erased, 2, 3, 4 steps, because there's 4 bit locations. So what you get here, the other advantage here is basically it's a fixed conversion time. Again, less stuff than the flash simultaneous conversion. Advantage here is a fixed conversion time in contrast to our dual slope, which if you had a high voltage here, took a lot longer for it to read that thing because it's basically using a counter to determine the magnitude. Okay, so successive approximation, the way I like to think of this too is pretend you're a kid with a bunch of holes, square-shaped holes in a piece of board, and you got your blocks that you're trying to fit through that thing. I know this isn't exactly how it works, but this is the way I like to think of it. If this block fits through that one, chances are it's smaller than that one, so move on to the next one. If it fits there, you're good. You know, if it fits exactly there, you're good. But if it fits through that, may require some of the area of that one. That's what I'm using this example kind of here. May require just a little bit more area. So I guess the blocks example is not so good. But whereas if this big old block right here doesn't fit through that one, it requires a little bit more area. So you have to summate that one, and maybe that one, and maybe that one for this thing to fit through. Yeah, not exactly the most apropos example. Because again, I know how you guys played with blocks. If the block didn't fit, you just hit it harder. Okay, final one. What was our final one? What are we doing here? Oh, sigma delta. Okay, sigma delta. Analog to digital conversion. This guy is basically a serial stream of ones or zeros. And basically, for each sample interval, all you do is send a bunch of ones and zeros depending on the magnitude of that zero, of that sample value. I.e., the more ones, the more positive the signal. Less ones, more negative the value might be. If it's even, zeros and ones, it's got a 0 value. So if you're just sitting at 0, 1, 0, 1, 0, 1, let's just draw that. So 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1. Notice how I'm not saying anything because it's 0. 0, 1, 0, 1, 0, 1. And now watch this. So if 0, 1, 0, 1 means 0, this, by the way, is 0. If it's 0, 1, 0, 1 means level 0. What is 0, 1, 1, 0, 1, 1, 0, 1, 1? Is it more positive or more negative? It's more positive because there's more ones. Now I say 0, 0, 1, 0, 0, 1, slightly negative. Okay, so you get what's going on there is basically the more ones you send in a specified time interval there. Let's just say for every 1 second, these things are 1 second blocks there. In 1 second, if you send me 4,000 ones in 1 second, I know that I'm up here. If you send me 2,000 ones and 2,000 zeros, I know I'm right there. If I get 2,000 zeros, I'm right here. Okay? If I get a little bit more ones in that 1 second, like I get 3,000 ones, I'm somewhere in the middle between a 0 and a maximum. Okay? And how is this all done? Well, you've got this circuit right here in your book. The key thing is our counter here. Basically, 4,000 ones come in. Basically, our counter is going to register anytime you get a 1 coming in there. 4,000 ones, 4,000 equals a maximum positive value. And basically, this thing right here is a summing point. So a plus and a minus. So summing a negative value, this means you're subtracting it there. If your input and what you're at currently, if there's a difference here, basically it's going to say add a 1 to it. If there's a difference, add a 1 to it. If there's a difference, add a 1 to it. Basically, that's what that feedback is. And now, if there is no difference, stop adding ones. Don't have zeros. And that counter's not, excuse me, just have zeros. Don't have ones. That counter's not going to register. Okay, all of a sudden, your input comes up a little bit there. Okay, add a 1 to it. Okay, we're good. The counter's registered just that 1 bit. So sigma delta, analog to digital conversion, use a little bit of a feedback and our counter. Key thing is, the more ones you get, higher positive value. The less ones, lower value. Okay, let us finish up analog to digital conversion, talking about some testing. Obviously, one of the more common ways of testing these things is to just go ahead and give it a ramp circuit from 0 volts to, let's say, your maximum is 15 volts. Your analog to digital converter should produce something. I know it's a nice slope like that, depending upon your resolution. Let's say we've got a 16-bit resolution. We should have, 16-bit, I'm sorry guys, 4-bit resolution. We should have 16 natural steps indicating 0 to 15 volts. Okay, so that's what you would expect. But you might get a missing value there. So notice that skip step right there. So that's 0, 1, 2, 3, 4. 4 volts stays at 4 volts and then goes to 6 volts. So for some reason, that 5 position is missing. And I don't know why. Maybe you got a wire in there or something. The other thing that's common in analog to digital conversion errors, let's say you have this 4-bit and you're putting in a ramp, an analog ramp, and you go 0, 0. When you should be going to 0, 1, something's wrong there. Then you go up to 2, and you should be going to 3, but you're staying at 2. And now you're up to 4, and you should be going to 5, but you're staying at 4. For some reason, what's happening there, normally, let's just draw what you would normally expect. You'd expect those intermediate steps. What's wrong there is your lower order, your LSB, is inadvertently grounded. Notice how your code 0, 0. You would normally expect a 0, 1 there, but you're getting a 0, 0. 1, 0, and normally you would expect a 1, 1, but you're not. Getting a 1, 0. So missing codes or something that's often stuck in a position, either 0 or 1. That's a common analog to digital conversion error. The other thing that you should be aware of is these offsets. Okay, so our analog 0 to 15, good to go, but check this out. Let's say what you're getting here is 3. There's a bunch of steps here. To 18. So if a 0 converts to 3 and a 15 converts to 18, what you've got is an offset error. Okay, so what might be happening here is for some reason you're inadvertently adding 0, 0, 1, 1 to every particular conversion there. Okay, so offsets. There's also something like a gain error. Like, let's just pretend what I'm about to draw is a digital step here. Initially, it's pretty close, but as you go further, it gets worse and worse. Same thing here. It's a positive gain error. That's a negative gain error right there. So things may start off okay, but then get worse and worse as time goes on. So missing codes, offset errors, incorrect codes, and our gain. There's no limit to the errors you can create with these guys. All right, let's go on to the opposite, namely digital to analog conversion, DAC. And that's where we're actually going to use this portion of the lecture right here about our magic device, the op amp.